Section 12.4 is about surface area. And before we get into that, what I'd like to do is in one place write out all the properties about area and volume we've learned for integrals, and then put the property for surface area right at the end. That way you have a convenient place to reference in your notes that has all these properties at once. So these are going to be kind of a recall, but you can just write them as a nice list for yourself. So to find the area of a region R, we take the double integral over that region, and we integrate 1 over that double integral. And you could take that double integral in any coordinate system you like, Cartesian or polar. So if you wanted to find volume under some surface F, above some region R, you could do this, a double integral over the region R of the function F, a double integral, or to find volume between two surfaces F and G above R, which is usually the region of intersection of the two surfaces. Then you take a triple integral that starts at G and ends at F of 1. This is a triple integral, so we do dv. That could be dx, dy, dz, or r, dr, d theta, dz, or rho squared sine phi, d rho, d phi, d theta, whatever you want. So those are two different ways that we learned how to compute volume, one using a double integral just up to some function f, and then the other using a double integral between two functions f and g. So that's just the difference there. We've gotten practice with both those things. And then our new property that we're going to learn today is to find surface area on some surface F above a region R. What we're going to do is we're going to take a double integral over that region R, and this is going to be double integral, so dA, but then the quantity that we integrate is special. It's going to be f sub x squared plus f sub y squared plus 1. And so this is the new thing that you really want to make sure to get down in your notes, but I thought it would be helpful to have all 4 of these things in one place. That way, anytime you have an area, volume, or surface area type problem, you can go here and pick the easiest way to address it. Now we're going to talk a little bit more about this equation and what it means, though, so you actually know how to use it. So just to be clear about the problem we're thinking about, the idea is that we've got some surface that we're going to call F. So we plot it by taking z equal to f of xy. And then over some part of that surface, we're wondering about the surface area. And if we project that part of the surface down into the xy plane, it's above some region R. But the region R isn't the same size as the area. This is easiest to imagine with very bendy things. So something that has like a big bend to it, if you carve a little chunk out of it that has a relatively small rectangle, it can be a very big part of the surface, kind of how um, like wedges of a pineapple are shaped like this thing that I just made because, the outside of the pineapple is bigger than the inside of the pineapple, kind of like that. So our problem is to find this surface area. So you'll always be given f of xy for the surface. Or it's an easy one. So for example, you should know the f of xy that gives you a sphere. So maybe somebody would just say find surface area of sphere, and then z equals square root radius squared minus x squared minus y squared. And you need to project down into the xy plane to find your region R. Sometimes if you have two surfaces that are intersecting, you solve for that. To get your region R, we've seen a lot of examples like that, especially if that intersection is with the xy plane. Then you're just setting your surface equal to 0. If you're not given an intersection, usually you'll be given a description of the region R more directly. So there's less to worry about there. And then you need to take your partial derivatives of the function for your surface. To calculate this quantity. And from there, you just evaluate a double integral. I'm not going to show this to you, but I just want to tell you so that this doesn't feel like it's coming out of nowhere. Remember when we learned about like curvature and arc length and all that stuff using like position vectors? This function that gives you surface area uses the exact same principles. So we could actually write this function as a like position vector type problem, but the easier way to deal with it is with this formula right here. And so that's what we'll do. But if you're curious about why this works, you can ask me about it, come to office hours, whatever. But it's basically the same way arc length works. All right, so we're going to do some examples next.